The session on algorithms theory and optimization. I'm Amin Karbasi from Yale University. I'm going to chair the session. So I'll ask all the speakers to actually be in the front so that we can have a smooth transitions between them. For the spotlight talks, we're going to use only one computer, but for the oral session, for the oral talks, we're going to use the speakers' computers. So we'll have 14 talks in total. 2 of them are going to be oral. Okay, very good. So the first one is nearest neighbor information estimation.
Thank you for the introduction, and good afternoon, everyone. My name is Wei Hao Gao from UIUC. This is a joint work with Jian Tao from Berkeley and Yanjun from Stanford. We are talking about the nearest neighbor information estimator is adaptively near minimax rate optimal. So let's first define our problem. What is differential entropy? So differential entropy of a continuous random variable is defined as the integral of the density times log 1 over the density. It's a kind of a generalization of the classical Shannon entropy for a discrete random variable. And it's very useful in various machine learning tasks, including classification, clustering, and feature selection. It's also useful in many other areas, such as causal inference, sociology, and computational biology, and many others. In this paper, what I focus is the estimation of differential entropy. Assume you are given some empirical samples x1 through xn RID from the density f. We want to estimate the differential entropy of f. So one of the classical and very important idea of differential entropy estimation is the idea of nearest neighbor method. So assume that we have RIK is the L2 distance from xi to its k nearest neighbor, and the volume dr is the volume of the dimension ball with radius r. An empirical observation is that the density at xi times the volume of the ball with radius rik is approximately k over n, because there are k out of n samples inside this ball. So using this observation and plugging this to the formula of differential entropy, we will have a nearest neighbor estimator of differential entropy. Kozachenko and Leonenko shows that besides the plug-in estimator, we still have to use a bias correction term of log k minus phi k, where phi is the digamma function. So KR estimator is the most widely used estimator for differential entropy, especially for high dimension, because of the following. Okay, sorry. First, KR estimator is very easy to implement. All you need to do is fix a k and compute all the k nearest neighbor distances. And you only have to tune one hyperparameter, which is k. And also, it has shown very good empirical performance without, especially in high dimension. But we still, the theoretical guarantee of KR estimator is still not complete, especially when the density may be very close to 0. So in this paper, we are working for this. Here is our main result. We assume that the density lies in a hypercube in a high-dimensional space, and the density is S Holder smooth. We can prove that the L2 error of the KR distance has a rate of n to the power of minus S over S plus D log n plus n to the minus 1/2. So as far as we know, this is the first theoretical guarantee for this K-error estimator of differential entropy without assuming the density is bounded away from 0. And this is very important. Another significant of our result is our results match the lower bound with, within a polylog factor. In the previous paper, we have shown that for any density differential entropy estimator, the L2 error has a rate greater than this formula. So we can see that our upper bound is close to the lower bound within a polylog factor. So here are some take-home message. In this paper, we prove that the nearest neighbor differential entropy estimator is nearly minimax optimal. Also, the differential entropy estimator doesn't have to know the smoothness parameter S. Unlike some other rate optimal estimators who will need to know the smoothness parameter, we only need one parameter K, which makes this estimator very practical. And the technical we use to deal with the small density is the maximal inequality. So please visit our poster number 86 tonight. Thank you very much.
Thanks, everyone. My name is Yash Deshpande, and I'll be telling you about contextual stochastic block models. This is joint work with Andrea Montanari, Elkanan Mosel, and Shubhabrato Sen. So let's go back to our first machine learning class when we learned how to do clustering. There's roughly two ways we know how to do it. One is when the data is represented in terms of similarities between objects. So this is the picture on the left, where rows and columns represent objects, and the particular entry is how similar these objects are. And what we want to do is to resolve it into two coherent sort of groups or clusters, like you can see what I've done with the rows and columns on the left. The other is a feature-based approach where each object is represented in terms of a number of different features. So this is the picture on the right. Each column represents a feature, and each row represents an object. And we want to resolve them using the features that are given. So this paper started when we wondered what would happen in applications where you have both of these sorts of data and they give you complementary information. In particular, you can have network data where each node also comes along with a number of different covariates that give you some more information apart from the graph topology that the network provides. So I'm going to tell you about a very simple statistical model for this. So I'm going to think about there just being two latent clusters and encoded as plus and minus 1 in a vector v, which is going to live consequently on the hypercube. And conditional on this vector v, I draw a graph where nodes are more likely to associate with each other if they're within the same group as opposed to outside. And the amount of this association, the difference, is quantified by this by the quantity that's lambda. And similarly, I'm going to think of the covariates as being drawn from a Gaussian mixture model with two components, and each component is basically identified with one of the latent clusters. So if you're in one cluster, you get a sample from one of the components of the Gaussian mixture. Otherwise, you get a sample from the other component. So the reason I chose one of these models is that actually both of these models are perfectly well understood. We know a lot about them. In particular, we know that you can estimate the latent clustering very well, given only the graph data, if and only if the signal-to-noise ratio quantified by lambda, this is the difference in the affinities, exceeds 1. And this is a sharp information theoretic transition. And similarly, we also know this for the covariate data, where if you just threw away the graph and talked about the covariates, you'd be able to estimate it if the distance between the centers that's quantified by mu squared exceeds the aspect ratio of the covariate matrix, which is basically n over p. What our result does is that we can combine both of these phase transitions. So at least in a mean field sort of limit where the graph is dense enough, we can show that you can recover the latent clustering information or the latent clustered information that's present in both of the data, provided the sum of these two SNRs or signal-to-noise ratios exceeds 1. In particular, what this means is that there's a regime in which each individual piece of the data is not useful to recover the clustering, but when you combine them, you actually get non-trivial information out of it. So there's a lot more I can tell you offline. And at my poster, it's number 79 in one of the rooms downstairs. Thank you very much.
Hello, everyone. Nice to see you again. So this talk is not mine, but unfortunately, none of these authors are here because of visa reasons. So I will be presenting their work. So this work is about entropy rate estimation for a Markov chain with a large state space. So let me first define what is the entropy rate. So entropy rate of a stationary random process is defined as the Shannon entropy of xn divided by n, take the limit as n goes to infinite, where the Shannon entropy is defined as the summation of the pxn times log 1 over pxn. Entropy rate serves as a fundamental limit of the expected logarithm loss when predicting the next symbol given all path symbols. So it is related to NRP task. And it also serves as a fundamental limit of data processing for stationary stochastic process. So in this paper, the task is similar as our previous paper. Given a length n trajectory of the random process, we want to estimate the entropy rate. So what's the relation between entropy rate and the classical Shannon entropy? The relation is if the random process is an IID process, then the entropy rate is equal to the Shannon entropy of the random variable. So in the previous work, they have shown that for the discrete entropy estimation with a support set S, consistent estimator exists if and only if the number of samples is greater than S over log S. So let me show you in this picture. So if the process is an IID process, the sample complexity is S over log S. So if the process is a constant process, which means every random variable is the same, so no matter how many samples you get, you cannot estimate the entropy rate. So sample complexity is infinite. So this paper I want to solve the problem in between. So the assumption is that the random process xn is a reversible first-order Markov chain with a relaxation time tau. So the relaxation time tau is the inverse of the spectral gap, which characterizes the mixing time of the Markov chain. So if this process is an IID process, relaxation time is 1. If it's a constant process, relaxation time is infinite. So also we want to focus on the high dimensional setting where the state space S is very large and it may also scale with respect to n. So for the estimators, here we propose two different estimators. Notice that for the first order Markov chain, the entropy rate is exactly equal to the conditional entropy of x1 given x0. And further, we can write it as the summation of pi I, which is the stationary distribution times the conditional entropy x1 given x0 equal to I. So we have to do two things. First is the estimation of pi I. We can use the empirical frequency of state I. The second is the estimation of the conditional entropy given x0 equal to I. We can estimate this use the discrete entropy estimator. So we compare two different estimators of discrete entropy. The first one is the empirical estimator, which you plug the empirical estimator of the probability into the formula of Shannon entropy. The second is the optimal estimator proposed in the paper before. The main result of this paper is shown as follows. For the empirical estimator, if the relaxation time is greater than threshold, your sample complexity is greater than S squared. If it's smaller than the threshold, your sample complexity is S squared. So for the optimal estimator, if the relaxation time is greater, your sample complexity is greater than S squared over log S. If it's smaller than some threshold, it's smaller than S squared over log S. But for a wide range of the relaxation time, our sample complexity is exactly S squared over log S, and it doesn't depend on the relaxation time. And here is the application for the language model. We compute the cross entropy loss with the fundamental limit of the cross entropy loss versus the state of the art. For Pentry bank, we can say that the fundamental limit is 1.5 bits per word, and the state of the art is 5.96. So this will be, the poster will be number 82, but unfortunately no one will be presenting the poster. Okay, thank you very much.
I'm going to talk today about a novel convex relaxation for a challenging bilinear recovery problem coming from image processing. And this is joint work with Ali Ahmed and Alireza Agassi, and it concerns the blind deconvolution problem when coupled with the phase retrieval problem. So mathematically, this problem is formulated as follows. Suppose I have two unknown vectors, which are real or complex, and call those W or X. And my goal is to recover W and X from the square absolute value of the Fourier transform of the convolution of these two signals with each other. And note, neither of these signals are known in advance. Right? This is a challenging problem because there's two sorts of information loss. First, the absolute value measurements mean you lose complex phase information. And second, the bilinearity means that you only have measurements of the product of two signals as opposed to the entries of each signal individually. These bilinear inverse problems come up in computer science tasks, such as sparse coding, dictionary learning, and non-negative matrix factorization. In order to make this problem well posed, we have to assume some structure on the signals, and we'll assume that they live into fixed and known low-dimensional subspaces, which we'll call given by the range of B and C, and the coefficients of these vectors in those bases will be H and M. So we can write this problem as a feasibility task, which is non-convex. Right? So in particular, the observations that we have are really quartic measurements of these unknowns. Right? Because of the Fourier transform and its relationship to the convolution, the ELF Fourier mode that's measured is really some vector that is known BL dotted with H, absolute value squared, and the product with some other vector that is known CL dotted with M, quantity squared. Right, so the standard convex relaxation approach to this would be to lift this to a matrix recovery problem and then to lift that to a fourth order tensor recovery problem. So as we see on the bottom of the slide, we could write this as the task of trying to find the coefficients that are the smallest in L2 norm that are consistent with the data, and we could use a standard trick of lifting, which is to say, instead of looking for the vectors H and M, look for the matrices HH star and MM star, and the quartic measurements are now quadratic measurements in those matrices. So that's the trick of lifting. And so we could try to make a convex relaxation using the standard semi-definite relaxation. So in this lifted matrix space, those rank 1 constraints are standardly approximated by positive semi-definite constraints, and then the L2 minimization can be replaced by trace minimization. Unfortunately, the quadratic measurements of these unknown matrices are non-convex, and they have a hyperbolic character to them, and the feasible set actually in high dimensional space looks sort of like these hyperbolas that are depicted. So now, the standard approach of how to deal with that would be to lift again to a fourth order tensor rank 1 completion problem, but the tools for that are not as well developed as matrix completion problems. So here's where the novel convex relaxation that we introduce comes from. We'll notice that in the first term of these constraints, both of those terms are positive, which is to say that these hyperbolic measurements actually only live in the first quadrant. And so then there's a non-trivial convex hull of that branch of the hyperbola. And so the program, which was non-convex, can be made convex simply by changing the equality constraint to an inequality constraint. As some of you may know, this is actually strongly inspired by the phase-max work, both of Bahmani and Romberg and Struder and Goldstein. And it's a nice trick in this hyperbolic measurement setting introduced by the same authors in a method called branch hull. Right? So the geometric picture of what's going on is that the The optimization problem has a feasible set given by these hyperbolic measurements. Those are depicted in red. The PSD cone is depicted in blue, and the minimization problem finds the point closest to the origin that's in the intersection of these, which lies along this pointy ridge of this feasible set. Right. So this paper introduces a rigorous recovery guarantee, which is to say that if you solve this convex program, then you get exactly the right answer, provided that the number of measurements is proportional to the number of unknowns. We additionally do some numerical experiments to show that the constants are not so bad. And while it's important to take the results of this paper with care, because this problem subsumes both the phase retrieval and the blind deconvolution problems, which are both challenging. And nonetheless, we hope that it inspires new approaches for bilinear problems in computer science, such as non-negative matrix factorization.
Okay, the first oral talk is going to be on stochastic cubic regularization for fast non-convex optimization, and Nilesh is going to present this very cool work.
Thanks for the introduction. So today I'll be telling you about our recent work on developing a stochastic method for non-convex optimization. This is joint work with Mitchell Stern, Chi Jin, Jeff Rogier, and Mike Jordan. So to begin, as most of you are probably familiar with, many problems in machine learning can be phrased as optimization problems. This might happen, for example, if you're doing empirical risk minimization and you're trying to minimize the loss function of a neural network. But it could also happen if you were doing variational inference, for example, and you were searching over a space of parameterized probability distributions to approximate a more complicated intractable probability distribution. However, usually two additional complications arise. First, the function is usually observed noisily. That is, we can't usually evaluate the entire function itself. For example, if the loss function was a loss function of a neural network evaluated on a huge data set, we might have to subsample that data set for tractability. Additionally, the data might be arriving in an online fashion, so we might not actually have access to the entire data set all at once. Secondly, most functions in machine learning tend to be non-convex. So to frame the problem, it's useful to recall the familiar setting of convex optimization. Convex problems have a very nice property that local geometric information, in fact, allows you to conclude something about what the global minima is. So in fact, if you can find a point where the gradient vanishes, a so-called first-order stationary point, you can in fact certify that X is a global minima. In the setting of non-convex optimization, the situation is a little bit more complicated. So here, if we can find a first-order stationary point, equivalently a point where the gradient is 0, or the function looks flat, it can be a local minima, a local maxima, or a saddle point. So in general, unfortunately, the task of finding global minima for arbitrary non-convex functions is just too hard. We can't solve this problem in general. However, you could still ask if we can solve a slightly more refined question. That is, instead of just searching for first-order stationary points, can we in fact design algorithms to find local minima? Or in other words, can we design algorithms that can provably escape saddle points? And if so, moreover, how fast can we do it? And by fast, here I mean in terms of iteration complexity. So how long does it take for the algorithm to actually find a local minima in terms of the number of queries it takes on the original function itself? So with that in mind, it's helpful to think about one of the simplest algorithms in machine learning, the gradient descent algorithm. And you might wonder if this algorithm in and of itself is already good enough to find local minima. So it turns out, in its original formulation, the gradient descent algorithm and its stochastic counterpart, SGD, can only find stationary points and not local minima. However, thinking about the stochastic gradient descent algorithm or the gradient descent algorithm will actually motivate the central algorithm of the paper. So it's helpful to consider a simple reformulation of this algorithm before we proceed. So another way to think about what the gradient descent algorithm is actually doing is at each step, you're actually solving a local quadratic subproblem. So the gradient descent algorithm can be thought of as minimizing the first-order Taylor expansion of the function itself plus a quadratic remainder term. And it's in fact just one line of algebra to show this. And one optimization problem we all know how to solve is how to minimize a convex quadratic. And so if you take that convex quadratic, you just set the gradient of it equal to 0, and do a couple lines of algebra, you can rearrange this expression to recover the gradient descent algorithm. And this view on the gradient descent algorithm is pretty powerful because it in fact motivates the analysis of the algorithm, where you basically show that this quadratic submodel is in fact an upper bound on the function itself. And so what the gradient descent algorithm can be thought to be doing is actually iteratively minimizing a series of quadratic upper bounds on the function. So this graphical depiction also explains why the gradient descent algorithm can, for example, get stuck at a local maxima of the function. And if you can see this picture right here, if you're at a local maxima, the quadratic upper bound doesn't actually capture the local geometry of the function very well at that point. So this brings us to the central algorithm of the paper. You might wonder, given that we're only minimizing a local quadratic approximation to the function, if we could minimize a higher order approximation to the function and obtain a better algorithm. And this is exactly the question that Nesterov and Polyak ask in the cubic regularized Newton method. So in the cubic regularized Newton method, we actually now take a second order Taylor expansion of the function and we add a cubic remainder term. And so this local model actually explicitly incorporates Hessian information of the function into the local model that it tries to solve. And as you can see, for many functions, for example, if you're stuck at a local max, this upper bound is in fact a tighter upper bound on the function, and it sort of more faithfully represents the local geometry. And so if you were able to exactly minimize this, this in fact leads to an algorithm that can provably escape saddle points and find local minima in the non-stochastic setting. So there are a couple additional complications here. One is that as you see this green cubic submodel, which represents the cubic polynomial, this function itself is non-convex. So it's not clear at first pass why this is actually easy to iteratively solve at each iteration. But it turns out that although this submodel is non-convex, and in fact this cubic polynomial doesn't have a nice closed form solution, which we do have in the case of gradient descent, for example, you can actually exploit a lot of special structure in this problem to derive fast iterative algorithms to solve this problem. And in fact, there's actually a version of strong duality that holds for this problem if it's rewritten in the correct way. So you can actually get a handle on this problem itself to solve. So now, before we move on to the central algorithm in this paper, it's helpful to more formally recall what our goal is. So to do that, we should actually define what is an epsilon approximate local minima, or what's also called an epsilon approximate second order stationary point. So such a point is a point where not only is the gradient small, but the minimum eigenvalue of the Hessian is not too negative. And so with this in mind, this brings us to the central question of our paper. And that is, can we design a stochastic cubic regularization algorithm? And if we can do so, how fast is such an algorithm in terms of finding a local minima? And by fast, we mean how many queries to the function itself does it take to actually return, for example, an epsilon approximate local minima of the function? So here we have just some pseudocode for the algorithm, and we'll walk through every line, and we'll interpret what all of this means. So first of all, this is a very bare bones version of the algorithm, so a lot of details have been stripped out. But at a high level, this is actually a double loop algorithm. So in the outer loop, those represent each of the outer steps of the algorithm, where in each step we try to approximately solve a local cubic submodel. So in the second and third lines, what we're doing is we're stochastically approximating the gradient of the function to obtain gt, and then in the third line, we're taking a stochastic approximation of what we'll call a Hessian vector oracle. So bt itself represents the true Hessian, but the algorithm actually never needs to build or construct the full Hessian at each iteration. So using this, you can construct a stochastic approximation to the cubic submodel, which was the green line that we saw in the earlier graphical depictions. So given this, what we'll do is we'll run an approximate subsolver on this model, which here we're referring to as basically doing something that's roughly doing gradient descent. And this will return an inexact solution to the stochastic submodel. And with this solution, we can get a candidate update for where to move in terms of the whole space. And this is what we'll add to our original iterate xt to update to the new point xt plus 1. So graphical description of this entire process we can see in the next slide. And so if we consider the original non-convex function f of x, what the full batch cubic regularized Newton method would do is minimize this dashed green line, which is given by mt of y. And ideally, if we could find the global minimizer of that, y star, we would be in good shape. But in our setting, we can only minimize or consider a stochastic approximation to this cubic submodel, which we refer to as tilde MT of y. But even in this model, we can't exactly solve it to infinite precision, so we have to settle for an approximate solution, which we call approximately y star tilde. And so it turns out if you control the errors from all these approximations, you can get a convergence guarantee for this entire algorithm. And this is the central theorem of the paper, which roughly says that under some regularity conditions on the function, which are standard in this literature for algorithms that can provably escape saddle points and find local minima, and some standard assumptions on the noise model, the stochastic cubic regularization algorithm will output an epsilon approximate local minima in roughly epsilon to the negative 3.5 iterations. And so the total algorithm itself only requires gradient evaluations and Hessian vector evaluations from the original function. And Hessian vector products can roughly be computed in about 2 times the cost of gradient evaluation. So they're roughly about the same cost. So for some context for what this guarantee means, it's helpful to think about SGD. And although SGD itself can't find local minima, it turns out by injecting noise into the process, a version of SGD called perturbed SGD can find epsilon approximate local minima in epsilon to the negative 4th poly d iterations. And so finally, I'd like to just briefly conclude with an experiment. And so in this experiment, we trained a deep autoencoder on the MNIST data set. And this is a problem that will have quite a few saddle points in the landscape. And it turns out that the cubic regularization algorithm, at least for this example, can perform better than some other commonly used algorithms that also have theoretical guarantees. So with that, I'd like to conclude the talk, and I'd like to thank everyone for listening, and of course, my wonderful collaborators who are listed above.
Actually, we have some time for a few questions. So there are 2 mics if you have some questions to ask. So let me just ask the first question.
No.
So I think the problem was unconstrained, right?
Yes, the problem is unconstrained.
So do you have any?
Oh, insights about constraint?
Right.
So that's a good question. I think most algorithms currently that people study for escaping saddle points and finding local minima are in the unconstrained setting. I actually think there's a paper at NeurIPS that's working on the problem for solving it in the constrained setting. But I don't think there's, for example, a generalization of the cubic regularization algorithm for constrained problems yet. So I think that work is just beginning.
Right.
Yeah.
And is there any variance reduction?
No, so that's actually a good question. So the algorithm as presented actually uses no variance reduction techniques. And many algorithms in non-convex optimization that tend to have good rates actually explicitly use variance reduction. So I guess that's kind of an interesting theoretical feature, is that no variance reduction is used to obtain the rates for this algorithm.
Uh-huh.
Yeah.
Okay.
I can answer your question, I mean. So
okay.
It's actually impossible to get to second-order stationary points for constrained problems, because that includes copositivity as a special case. And given that copositivity is NP-hard, it suggests that doing it more generally will remain challenging.
I see. Okay.
So.
Thank you. Yeah. Good. Okay.
Can I ask a question? So, in this work, you consider adding a cubic term in the sub-optimization problem,
Yeah.
right? So, I think it's very similar to mirror descent. Like, can this formulation be rewritten in a mirror descent way?
So, not that I'm familiar with. So, do you mean like mirror descent has like a Bregman divergence term added to the gradient or something like that?
Yeah, you choose appropriate mirror map. And,
yeah, I don't think there's a mirror descent interpretation of the cubic regularized Newton method as far as I know. So the other thing is mirror descent only explicitly uses first order information from the function. So that's another difference, whereas here there's also like a Newton term. For example, you saw the Hessian explicitly appear on that slide. So I don't believe the cubic regularized Newton method has such an interpretation.
So you think it's impossible to do it?
Yeah, I don't think it's impossible to rewrite it as. I don't think it's possible to rewrite it as mirror descent, if that's what your question was.
Yeah. Okay. Thank you.
Do you have thoughts on the inductive bias of this algorithm? Say the types of global optima that it finds?
Oh, the types of local minima that it finds?
Yeah, as opposed to, like in terms of generalization.
That's a good question. Intuitively, I don't have a good sense. I mean, I think a large class of problems, people know that, for example, local minima are global minima, but that's a problem-specific result. And for other problems, people also know that local minima tend to generalize well. But those are more problem-specific results. I don't actually have a good sense of what types of local minima the algorithm can find, as opposed to, for example, other algorithms. But it's an interesting question to think about. Yeah. Cool.
Okay, very good. Okay.
Thank you.
Yeah, let's thanks the speaker again. And again, for the oral, for the spotlight presenters, please just come, sit on the first row so that we can, have a smoother transition. Okay.
Hi, everyone. I'm Donghua Zhou from UCLA. This is a joint work with Pan Xu and my advisor, Quanquan Gu. In this work, we focus on solving the following non-convex finite sum optimization problem, where we assume that each component function fi is L-smooth, and f has a stochastic gradient with sigma squared bounded variance. We also study the case where f is satisfied by the PL condition with the tau gradient dominated assumption. Since the problem is non-convex, our goal is to find an epsilon approximate first-order stationary point, or to find an epsilon approximate global minimizer if we have the additional PL condition assumption. Before we introduce our algorithm, we first briefly review some existing algorithms to find the first-order stationary points, including gradient descent, stochastic gradient descent, stochastic variance-reduced gradient, aka SVRG, and stochastically controlled stochastic gradient, SCSG. The updated rules for the above four algorithms can be written as the xt plus 1 equals to the xt minus the eta times so-called semi-stochastic gradient Vt. And from the table, we can see that the gradient descent and stochastic gradient descent, Vt, are merely the full gradient or the stochastic gradient at the current point. For SVRG and ACSG, things are a little bit complicated because Vt are constructed by the use of so-called reference point, where Vt can be regarded as the linear combination of a stochastic gradient at both the current point and its reference point. And from the gradient complexity comparison, we can see that the use of reference point is indeed helpful to reduce the gradient complexity. Inspired by the success of using the reference point, we propose our algorithm, SNVRG, which makes use of multiple reference points instead of one. Our algorithm consists of three parts. The basic part is SNVRG epoch, which will initialize k plus 1 reference points and reference gradients at the beginning. And at each iteration, it will update the reference points and the reference gradients by specific update rules, which will be revealed in the next slide. After getting all the reference gradients updated, it will take the summation of the reference gradients as Vt and use it to update the current point. For the main part, SNVRG, it iteratively runs SNVRG epoch and uniformly chooses one iterate from all the previous iterates. For the third part, SNVRG PL, which is used to find the epsilon global minimizer under the PL condition, it runs SNVRG at each iteration and outputs the last iterates. To illustrate the updated rules for the reference points and the reference gradients, we will use the following 6 tree-like figures to describe how our updated rules work for a very specific example where we take k equals to 2 and the update parameters t1 and t2 equals to 2 and 3. From the figures, we can see that the nodes at different dips represent different reference points, and the edges at different dips represent different reference gradients. For each reference gradient, it is constructed as the difference between the two corresponding reference points with the same stochastic batch. And for the reference points, they will be updated in different frequency up to the current point, which is denoted by the update parameters. It is also worth noting that the reference gradient will not be updated unless at least one of its reference points has been updated. Now we propose our main theoretical contribution. To find the epsilon approximate first-order stationary point from the comparison table and the figure, we can see that SNVRG is strictly better than the state-of-art results achieved by ACSG by a factor of the minimum value of n to the power of 1/6 and epsilon to the power of -1/3. Note that a similar complexity result has also been obtained in a concurrent NeurIPS work by Fang et al. Under PL condition, SNVRG PL is able to find an epsilon approximate global minimizer, and its convergence complexity is also strictly better than the state-of-art results achieved by ACSG by a factor of the minimum value of n and tau divided by epsilon to the power of 1/6. Thanks for your attention, and if you are interested in more details, please come to our poster session in number 14.4. Thank you.
Hello everyone, my name is Qijing. Today I'm going to talk about our recent work on the local minimum of empirical risk. This is a joint work with Lydia Liu, Ron Ge, and Michael Jordan. Okay, first, I guess a lot of people already talk about non-convex optimization. I will just go quick. Non-convex optimization can be much more difficult than convex optimization. So classically, we only know gradient descent is going to find a stationary point, where stationary point could be local max, saddle point, and local minimum. Fortunately, a lot of recent work has already been attacking the first two kinds of points, especially they have the same structure, which is like the right figure. At least one of the direction has a negative curvature so that you can escape from. So I guess one of the work is our previous work, which showing gradient descent, as long as you're adding some perturbation to it, it can efficiently escape both local maximum and saddle point, a large class of them. So the real question left is about the local minimum. Especially for the local minimum, you might have those global minimum, which is what you want, and also have some spurious local minimum, which are the local minimum that are not global minimum, which we call those spurious local minimum. So the big question is how to deal with spurious local minimum. Unfortunately, in general, you cannot say anything about it. In general, finding global minimum is NP hard. So the right question is you need to make some assumption and put some structure on a problem, and you say you're gonna escape some specific of local minimum. So the question we have been looking at is the one has been investigated in the community, is so-called avoiding shallow local minimum problem. So the problem is we have an underlying function, which is a black curve, which is kind of like smooth. We want to find the local minimum of that black curve. Unfortunately, we only have access to the right curve, red curve, which is kind of like zigzagging around black curve, and it can have a lot of spurious local minimum around it. So we want to escape those additional local minimum introduced by the zigzagging non-smooth red curve and find the local minimum of black curve. And one key assumption we make is these two functions kind of like point-wise close by arrow nu. Okay. So the first question you may wonder is why I'm interested in this kind of problem. So the most important application is in the statistical learning setting, where you want to minimize the population risk while you only have access to the empirical risk. Especially in the setting of a non-convex and a non-smooth loss function. And just remember, the empirical risk is an average over the data which you have, n data over the data set. And because L is non-smooth, so the empirical average is still going to be non-smooth. But a lot of times, because the underlying distribution has some smooth property, so when you're taking the expectation over the data under this underlying distribution, it's actually become a smooth function. So it satisfies our first key assumption, the underlying function is smooth. And the second one, the two empirical risk and the population risk is kind of like point-wise close, because a lot of reason in the statistical learning theory, you can upper bound it by Rademacher complexity, you can use uniform convergence. Okay. So now the question is we want to find epsilon local minimum of this black curve in polynomial time. So there are two central questions in solving this goal, in achieving this goal. The first one is what is algorithm that can achieve this? The second one is how much error they can tolerate. Because we know whatever the algorithm is going to work in this setting has to work on the setting where error is kind of like small. If error is too large, the two functions can be totally different, and there's no way you have some idea about this black curve if you only see the red curve. Okay. So the previous work, Zhang et al., which is the best paper in the code, and it's a very good paper. He first looked at this problem in a non-convex setting, and he proposed a sampling algorithm called stochastic gradient long-driven dynamics. He's saying this algorithm could work if arrow is smaller than epsilon squared over d to the 8th. In this work, we consider a more intuitive algorithm, which is an algorithm probably all the people are going to first think of when you see the problem. It's essentially you first do some smoothing on this capital little f red function, and then you perform an SGD with some perturbation. And we actually show this intuitive algorithm can tolerate much larger error. The tolerance is epsilon to the 1.5 over d. So we're actually better in both epsilon and d dependence. The second question you may wonder is, okay, you have this simple algorithm achieve this. Is that the best one you can do? Is there any other better polynomial algorithm can tolerate larger error? The answer is no. Actually, although this algorithm is simple, it's actually already the best among all the polynomial time algorithm. So basically, we can see in the middle, epsilon to the 1.5 over d is already threshold for SGD, but also like beyond that, no polynomial time algorithm could work. Although there are still some exponential time algorithm could work, but beyond epsilon to the 1.5, no, it's informally theoretical. So basically, this work also provided both polynomial threshold and also information threshold. If you're interested to learn more about this work, please welcome to our poster. Thanks.
Hello, my name is Richard Zhang, and this is joint work with Cedric Joss, Sumaya Sujudi, and Javad Lavai at UC Berkeley. Our paper studies the non-convex matrix recovery problem, which naturally arises in recommendation systems, but has a variety of other applications in engineering. So the basic gist of the problem is to express a low-rank matrix as the outer product of a low-rank factors, and to minimize the least squares loss of a linear model of the low-rank matrix. So this is a non-convex problem, so in general, a local search algorithm can get stuck at a spurious local minimum, and this results in failure. So it was a seminal result in 2016 that under a so-called restricted isometry property assumption, or RIP, that this problem contains no spurious local minima, and as a consequence, a local search algorithm is guaranteed to converge to the globally optimal solution. And similar ideas around RIP have been used to prove more general classes of problems, most importantly in the context of matrix completion. So this guarantee is actually relatively conservative. To really understand what this means, it's helpful to think about a matrix to measure the size of a matrix using its Frobenius norm. Then for this A operator to satisfy delta RIP with delta being less than or equal to 1/5 is to ask for the image of this map to stretch or shrink the matrix within 10%. Okay. So this conservatism naturally raises the question, can we do better? What we're really asking is, does the RIP assumption, is it strong enough to overcome the inherent difficulty, the inherent hardness of this problem? And in this paper, and we have many previous authors who have tried to improve this constant using a variety of different techniques, but in every single case arrive at a similar number. So in this paper, we give the first conclusive answer to this question. We show that beyond a value of a half, there exist numerous counterexamples. But furthermore, in the journal version of this paper, we give the first sharp guarantee that if your RIP constant is less than a half, then in the rank 1 case, we guarantee no spurious local minimum. So let's talk about some of these counterexamples. We have a counterexample with an RIP constant of a half. Consider these matrices here. And simply running stochastic gradient descent, we see that it really does get stuck at a spurious local minimum. And if we run this over 100,000 times, we see a failure rate of 12%. And we can generalize this into an arbitrary length n vector. And so the technique we do is we pose the problem of finding a counterexample as a convex optimization problem. Right? Using this technique, we actually prove something stronger. If you give me a ground truth, a pair of ground truth and a candidate point almost certainly I can find you a counterexample with a delta of greater than a half. And that's to say, in practice, this, once the delta is greater than a half, there's not too much we can do. What about less than a half, right? So we conjecture in the conference paper that, in this case, there's no spurious local min, right? In the journal version, we prove it for the rank 1 case. And sort of the proof technique, with a bit of work, we believe we can extend it to the general rank R case. So we believe the statement is generally true. Okay? But all this theory that I'm talking about, what does it mean for a practical recommendation system, right? So in order to answer this question, we engineered an example that purposely contained a spurious local minimum. And we started stochastic gradient descent, starting at the spurious local min and taking it further and further and further away from that point. And what we discovered was that there are many examples, right, where, you know, if you started from the spurious local min, then you result in 100% failure. But if you started from a random point, then you always succeed, right? The problem contains a spurious local min, but it doesn't seem to matter, right? But there are counterexamples as well. So in general, from a practical setting, right, local search might work, but we might just not be able to prove it. So in summary, right, in this paper, what we've shown is that sort of this RIP assumption, if the delta is greater than or equal to a half, it doesn't really say too much. But if it's less than a half, then we firmly believe that the problem contains no spurious local minima. Right? And from a practical setting, it's simply to say that local search might continue to work, but we need to develop newer tools to sort of analyze global convergence. And with that, thank you very much, and welcome you to come find us at our poster.
I will introduce our new paper, SPIDER, Near Optimal Non-Convex Optimization via Stochastic Pace Integrated Differential Estimator. We consider the following non-convex stochastic problem. We study both find sum case and online case. We are going to search an approximate first-order stationary point, and in the long version of the paper, we have also considering searching an second-order stationary point. The three pictures are all first-order stationary points. The third picture are second-order stationary points. We can find that to find a second-order stationary point, we must escape some saddles. And this is our result. Set online case as an example. To find the first-order stationary point, the standard SD algorithm leads a cost of epsilon to the power of negative 4. And the SVRG algorithm needs the complexity of epsilon to the power of negative 3.3, while our algorithm needs the complexity of epsilon to the power of negative 3. Also, to find the second-order stationary point, our algorithm also needs the complexity of epsilon to the power of negative 3, while other algorithms need the cost at least epsilon to the power of negative 3.5. This is our algorithm to find the first-order stationary point. We can find that the only difference in our algorithm is that we choose accumulated gradient in step 5, and we have chosen normalized step size in line 7. We have also proved that our algorithm have achieved the lower bound in find sum case. A similar complexity have also been proposed by Zhou et al. This is our core idea. To track a quantity that we are interested in, given an initial estimator, we instead integrate its stochastic differential estimator. So we call this technique as stochastic based integrated differential estimator. In war, we have proposed a technique named SPIDER. We proved that to find the first-order stationary point and the second-order stationary point, the complexity is epsilon to the power of negative 3. We have also proved that SPIDER matches the lower bound in finite sum case. This is inspired by Kammer et al. We have also considering to extend our algorithm to zeroth order optimization. Welcome to our poster in number 49. Thank you.
Okay, so we are going to have our second oral presentation by Yair on the analysis of Krylov subspace solutions.
Hello, everyone. Hello, everyone. This is joint work with my advisor, John Ducci. And I'm sure you've all come across, just a second. I'm sure you've all come across algorithms that have very strong theoretical guarantees, but unfortunately you look at the algorithm and it's very clear it's never going to work in practice. And on the other hand, you might have seen algorithms that are very, very good in practice, have essentially no parameters to tune, but it's very difficult to say theoretical things about. For example, LBFGS, and arguably also Adam. And if there is something I want you to take away from this talk is that there exists a class of algorithms called Krylov subspace methods for which this trade-off doesn't really exist. They are both very practical, have no parameters to tune, and you can derive very clean theory about with very flexible arguments. We did not discover this principle, it's fairly well known, but we give an example by analyzing a new class of problems that you can solve with these methods. So you've seen this slide in the previous talks. Our motivations is Newton's method that can be viewed as starting from a point xi, create a quadratic model, minimize the quadratic model, get the next point xi plus 1. The problem is that when the matrix, the Hessian is indefinite, this model is not bounded from below, so it's not clear what it means. However, we can regularize these problems. So from now on, the Hessian is going to be called A, and the gradient is going to be called B. And the trust region regularization is simply saying that there is an upper bound on the radius we're willing to entertain, and it looks like this. So now the minimum is well defined, and this is our next point. Cubic regularization just adds a cubic term to the quadratic objective, and again, the objective is bounded from below, and the next iterate is well defined. So when you iteratively solve a trust region problem, you get a class of optimization methods known as trust region methods. And similarly, for the cubic regularized problem, you get cubic regularization methods. Both of those are very well known, are very commonly used in nonlinear non-convex optimization, and have fairly strong theoretical guarantees. And recently, there's also been interest in applying them in machine learning, and in fact, the previous oral talk was exactly about that. Our focus is going to be how to solve these problems the most efficiently in the large dimensional setting where D is very large. And first, it should be said that if you are somehow able to factorize the matrix A, it only takes a few factorizations to solve the problem. However, in the worst case, factorization takes D cubed time. And even storing the matrix, if it's, say, the Hessian of a neural network with 10 million parameters, can be infeasible. However, what you can often do is compute matrix vector product. So you'll have some kind of box, you'll give it a vector, and you'll get the matrix vector product. And our focus is how many matrix vector products do we need to compute in order to approximate the solutions to this problem to epsilon accuracy. And this is where Krylov comes in, and this is Krylov at around the time that he invented the Krylov subspace solution. So a Krylov subspace is just the span of our vector B, and A times B, and A times that, and so on. And the idea of Krylov subspace solutions is very simple. In that subspace, find the optimal point. And it's actually very simple to do. So create an orthonormal basis for this subspace. And instead of solving for x in RD, solve for x tilde in RT and take x equals qx. So now the problems, instead of being d-dimensional, is only t-dimensional. Same for the cubic regularized problem. And this fits exactly our model because it requires only t matrix vector product. But it actually gets even better because there is an efficient recursion called the Langshus process that allows you to compute the basis Q such that the matrix Q transpose AQ is t-diagonal and therefore very easy to factorize. And most importantly, it is actually used in practice. So libraries for solving, for using trust region and cubic regularized optimization actually implement Krylov subspace solutions. And what we want to answer is how many of the iterations of these algorithms are necessary to solve the problem to accuracy epsilon. It's important to say that this is by far not the most significant things people do with Krylov subspace methods. In fact, if you have a large matrix and you want to do something scientific with it, you should think about Krylov subspace methods. The most prominent things is perhaps linear system solving. where conjugate gradient is a Kirchhoff subspace method, and so its generalizations to other types of linear systems. And Kirchhoff's original motivation was to find eigenvectors, and there the Kirchhoff subspace method is colloquially referred to as Langshos. You can also compute the product of the vector b with the exponent of a, and more generally you can view all of these problems as computing the product of b with some function of the matrix A. And all of these use cases have very strong convergence guarantees, and they're all intimately tied to polynomial approximation. And we show that the trust region and cubic regularized problems are no different. So to take a little step back about other works to solve these large-scale problems, in a previous work we've shown that for the cubic regularized problem you can in fact use gradient descent to solve it. This is a little bit surprising because it's a non-convex problem, but still you can. However, the rate is not optimal. Some other works have proposed algorithms for the trust region and cubic regularized problems that do get a stronger convergence guarantee. However, these are based on reduction. They basically solve this problem by solving a sequence of problems for eigenvectors and convex optimization. And I'm not aware of these algorithms being used in practice. In contrast, as we've said, the Kirchhoff subspace methods are extensively used in practice, but until recently there was no guarantee on the rate at which they converge. However, recently, Zhang et al. Gave a guarantee for the trust region problem, and now I'm going to discuss how we extend these guarantees. So our result apply for both the trust region and the cubic regularized problem, and we give two rates of convergence. The first rate of convergence is called linear convergence, and this is the rate that Zhang gave for the trust region problem. And this says that for a certain condition number that is kind of natural for the problem, the number of iterations to find an epsilon stationary point is essentially proportional to the square root of that condition number. The second type of convergence guarantees is basically is valid when the condition number is very large, so the first guarantee is weak, and it tells us that to find an epsilon stationary point, it is also sufficient to run a number of iterations proportional to the square root of 1 over epsilon. However, here there is an additional logarithmic factor that depends on the inner product between your vector b and u mean, which is the eigenvector of A that corresponds to lambda mean. However, there is also a possibility known in the literature as the hard case, where the inner product between u mean and b is 0, and the condition number is also very large. But there we show that using randomization, you can replace the logarithmic factor with the dimension of the problem d and get the result with high probability. And finally, we provide matching lower bounds that show that these guarantees are tight in the worst case for Kirchhoff subspace methods, and also via standard reductions, the deterministic algorithms that access A only through matrix vector products will in fact never do better up to constants. And now I'd like to focus on this guarantee and the trust region problem and just give you a sketch of our proof. So we write the suboptimality of any point x in the following form, which might look scary, but we actually just added and subtracted things. And then if you focus on the first part, you notice that this is actually convex in the variable x. So our first step is going to find a point in the Kirchhoff subspace to make this red term small. So here is how we're going to define our points. It's going to be t iterations of Nestorov's accelerated gradient descent to minimize this convex error under the constraint on the norm. Now, it might be a little bit surprising, but in fact, this algorithm produces a point in the Kirchhoff subspace, and therefore we can argue about it. Now, the only problem with this point is that its norm might be a little too small, so this norm error term might still be large. So what we're going to do is fix this by finding a different point x that will have a larger norm that will make this norm error term be exactly 0. So the ideal candidate here is this vector u mean. If we move in this direction, we can blow up the norm of y without hurting the convex error. And this is because the matrix A minus lambda mean will be insensitive to u mean, and the linear term can only be improved. However, u mean is not in the Kirchhoff subspace, but what we can do is we can rely on the fact that Kirchhoff subspaces are very good at approximating eigenvectors and use results about the Langshos method to show that there is a good approximation for u mean. So combining this, we have this point xt who has very small convex error and who has 0 norm error. So overall, it has very small suboptimality. And here is the nicest part. The actual solution in the Kirchhoff subspace is even better than xt. So combining all of these guarantees, we get our rate of convergence. Now, it's very interesting to compare this to the algorithm that Honoy and Killikhausen propose, because what they propose is very similar to this proof. They propose first computing an approximation for the eigenvector U mean, and then changing the problem by shifting the matrix A and actually running accelerated gradient descent. But they have to worry about how accurately to find the eigenvector, what step size to use for accelerated gradient descent, and we don't really care. For us, these are not just numbers that appear in the proof, and the algorithm itself, the Krylov subspace method, does not change. And this is really the reason why Krylov subspace methods don't sacrifice practicality for clean analysis. You can do all of these arguments in the analysis, and the final methods remain this simple Langshos recursion. So to drive this point home, here are some experiments. The gray lines are random problem instances. The x-axis is the number of subspace iterations. The y-axis is normalized suboptimality. And perhaps the first thing to note is if you only want a 1% multiplicative approximation, usually 20 iterations are enough. Moreover, for the lower condition numbers, you can see that our linear rate of convergence is quite accurate. And if we switch to a logarithmic scale, then you can see that the sublinear rate of convergence is also quite accurate when the condition number is high. So to summarize, you should pay more attention to Krylov subspace methods, regardless of whether you want to prove nice theorems or you want algorithms that actually work. You're all welcome to the poster to hear more about it.
Okay, we have some time for a few questions.
Great talk. So when you reduce using the Langshos to a smaller polymer, you use the orthogonality of the Q that Langshos generates, but that's only theoretically orthogonal. When you run Langshos, you get a Q that is not really orthogonal. How do you handle that?
Are you talking about numerical precision issues?
So it's basically just numerical errors. When you do Langshos quickly, the Q isn't really orthogonal, and you use that as in a reduction to make sure that your vector has a small norm. So yeah, in theory, everything is okay, but you run experiments. How do you handle the loss of orthogonality?
Yeah, so you'll notice that in experiments, we only run a maximum of 1,000 iterations, and it doesn't seem to be hurting us at this amount of iterations. Moreover, if you really want rough solutions, then probably 100 or even 20 iterations will suffice, in which case, at least from the experiments, I haven't seen that loss of orthogonality really hurts you.
So do you get solutions that are within the constraint set? Because orthogonality is lost very quickly, actually.
Yes. In our case, the constraint is very, very simple. You just need to compute the norm. So it seems to be doing okay. It's also, you can also think about it that we only care really deeply about the one extremal eigenvector, and that also is quite a bit more robust than getting the entire spectrum.
Okay, thank you.
So I also have a question. So there is the inner product between mu mean and in your bound, right? So it becomes 0. What happens to the bound?
So right. So if this term becomes 0, then this particular bound seems to become vacuous. However, since you notice it's a logarithmic term, it can actually become very, very small, and the bound isn't vacuous. So basically, one idea in order to solve this is to just add a little bit of noise to this vector B, and therefore you can assure yourself that now this inner product is not 0, it's something proportional to 1 over square root dimension, and this is how you can get the randomized rate of convergence.
And the bounds, do they have anything to do with the conjugate gradient or the guarantees? They look similar.
Yeah, they are very similar. In general, bounds for Krylov subspace methods tend to look similar. They tend to be the square root of the number of iterations required for a naive method. So the same happens here. And for the special case of, at least for the task region problem, in a special case that the problem is convex, you can actually run the conjugate gradient method and it will work.
Yeah, I have a quick question. So both of these problems are either unconstrained or have the sort of spherical constraint. Do you have any thoughts on extending it to linearly constrained using sort of the Krylov ideas, because it becomes like non-symmetric or indefinite, right?
Yeah, so I haven't spent a lot of time thinking about it. It might be challenging, depending on exactly how these constraints look like. You might be able to just transform the problem into a basis where the constraints are spherical, but I haven't really dug deep into it.
Thank you.
Okay, so let's thank the speaker again. And we are going back to the spotlight, right? And so we have a Natasha 2 paper, but apparently no one sent any slides and no one sent any information about whether they're presenting the work here or not. So if there is a presenter, please come forward. If anyone wants to present the paper.
Just go ahead with the program. This is the next one.
Okay, so then in that case, we can just go ahead with the program and have our second spotlight presentation.
Good afternoon, everyone. My name is Ali Jadbabai. I'm here to present the work of my postdoctoral associate, Aryan Mokhtari, and with my colleague, Asu Ozdaglar at MIT. So we heard a lot about non-convex optimization and escaping from saddle points. And in fact, the question was raised, what can you do if you have constraints? So this talk is precisely about that. So we're going to look at some very special cases in which we can do something about the constraint case. So again, I don't have to repeat this. We know in general non-convex optimization is hard. We're going to look at a case where we're minimizing a non-convex function over a nice convex compact closed set. And of course, as we saw in previous talks, that when the function is non-convex, first order optimality conditions is not enough because you might have saddle points. And essentially what you have to do is to check higher order derivatives to basically get out of saddle points. So a lot of the talks that we saw earlier and the oral presentation nicely described this and presented nice algorithms. And of course, we know that there are some very special cases of problems in which that all saddle points are escapable and or local minima are global. So we've heard some of that in this conference and previous meetings. Phase retrieval, dictionary learning, PCA, and some of these other things are special cases. So a little bit more formally, what you saw in the earlier talks, in the unconstrained setting, we call a point an exact second order stationary point if the gradient is 0 and the Hessian at that point is positive semi-definite. And of course, there are many algorithms that you heard about that talk about how one can escape saddle points and so guarantee that a point is second order stationary point. The other definition that was made previously in some of these references and was repeated today is that of an approximate second order stationary point. And the idea there is to say that a point x star is an epsilon gamma second order stationary point if the norm of the gradient is not too large and the smallest eigenvalue of the Hessian is not too negative. So we call that an epsilon gamma second order stationary point. And of course, we've seen here and in previous meetings that if you have in the unconstrained setting, computing an epsilon gamma second order stationary point is polynomial in 1 over epsilon and 1 over gamma. And so the question is, what happens if this problem you have convex constraint? And you saw in the question and answer session that John talked about matrix copositivity. So we know that there are cases in which even with simple ortho constraints, this problem could be hard because matrix copositivity, even though it's a convex optimization problem, can be posed as a convex optimization problem, is hard. But then there are special cases in which this problem can actually be tackled with. So this is what our poster is really about. So how do we characterize an approximate second-order stationary point? So now we have to first define it. There are multiple ways one can do it. The way that we've chosen is to use the supporting hyperplane characterization of an optimal point for a constrained optimization problem. So we know from our basic convex optimization course that the first order optimality condition in the constraint setting becomes that the gradient has to provide us with a supporting hyperplane to the constraint set. And then the second order point basically says that the Hessian has to be positive definite constrained on a particular subspace. So what do? Well, we use the same technique. We provide the same epsilon gamma setting. And so the question is, when is this definition now useful? Okay, so it turns out that there are some specific cases of non-convex problems for which we can use this definition using some recent non-convex advances. In particular, there are results in the OR literature where optimizing a quadratic non-convex function over a convex set can be done within a constant factor. So that's what we're doing in this poster. So long story short, one easy case is when the constraint set is ellipsoidal. So if you have one ellipsoid, the result extends fairly easily. And then you get this 1 over epsilon squared dependence, and d here is the dimension. Gamma was that parameter for the smallest eigenvalue. If you have m quadratic constraints, so you have intersection of ellipsoids, then the case becomes a little bit more complicated. You need some minor assumptions on top of that, and then you see this 1 over epsilon squared dependence again. And we have extensions of this to the stochastic setting as well. I'd be happy to talk to you about it in our poster session in about 15 minutes. That's poster number 47. Thank you.
Okay. So this is joint work with my colleagues from Dortmund, Alexander Montano and Christian Zola, and David Woodruff, who's at Dortmund, Alexander Montano and Christian Zola, and David Woodruff, who's at CMU. And I'm going to talk about core sets for logistic regression. So logistic regression is a binary classifier, a linear classifier, where this is the error function that you're trying to minimize over a labeled point set. And you can think of the error function, for those of you who are not familiar with it, as essentially being 0 if a point is correctly classified and being linear in the inner product between the point and the separating vector beta if it's falsely classified. And what we're trying to compute for logistic regression are core sets. So what are core sets? They are subsets of the original input point set X. They are significantly smaller in size, such that they behave for any candidate vector beta like the original point set would. So let's say this is our candidate vector beta, and the core set on the right here behaves roughly equal to the original point set on the left. And what is important about core sets and what makes them so useful is that I want this guarantee to hold for any possible candidate vector beta. So also if it's one that looks like it's nonsensical or not particularly interesting, I still want the guarantee. Why do I want this guarantee? Because it gives us black box reductions in distributed computing and streaming algorithms. Okay, so unfortunately, core sets for logistic regression in general don't exist, and they even do not exist if I'm only facing with one single class. So I don't even need two classes to show them. The hard instance is essentially this. So I arrange all points on the two-dimensional unit circle, and I can now linearly separate one point from everything else, make the norm of the beta arbitrarily large, so the cost is dominated by that one point. So essentially, I'm querying the entire convex hull, and I cannot really store the convex hull. So a sublinear size core set cannot exist for logistic regression in general. And this hard instance is, well, it's surprisingly robust to all possible variants of the problem. So whether I'm considering regularization or some other assumptions, this instance basically kills all core set notions that we have. So I wouldn't be here if I didn't have also something positive to say. So what can we prove? Well, if we cannot prove core sets in the worst case, the question what we can do beyond the worst case. So essentially here, we're only considering certain types of input. And the types of input that we are considering satisfy a stability guarantee that we, well, it is actually quite technical to define. It has something to do with the log odds ratio. But what you can essentially think of is if I'm given two distributions, then I would like to sort of have the total variation distance between those two distributions to be somehow lower bounded by a value mu. And now if we have such an input that satisfies the stability condition, we can actually compute a core set. So we can actually get a 1 plus epsilon multiplicative guarantee for any candidate input vector beta. And the algorithm, well, it's a surprisingly simple algorithm. So you just compute the SVD and you sample points proportionate to the square roots of the leverage scores of every individual point. And you repeat this sampling process recursively until you have subsampled essentially a polylogarithmic number of points. So this algorithm gives you a core set, 1 plus epsilon multiplicative core set of roughly this size right here. So the dependency on the original input point set is only n now. Okay, and what's nice about courses is that they not only reduce space, they also allow for a significantly faster computation. So we ran our algorithm on a number of input point sets, and the result is depicted right here. So to conclude, what's the takeaway message? So first off, we proved impossibility results for core set constructions for logistic regression in the worst case, but also introduced the notion of beyond worst case analysis for core set construction. And a few interesting open questions would be, one, directly relating to our work, can you perform the sampling procedure without recursion? So then you may actually get rid of the log n, or the log n to the 4. And the other question is more general, what type of beyond worst case analysis is meaningful? So is our notion of mu complexity the correct measure, and which other problems would benefit from a beyond worst case analysis for core sets? And that is all. Thank you.
So hi, everyone. I'd like to talk about Legendre decomposition for tensors. I'm Mashita Sugiyama from National Institute of Informatics in Tokyo, and this is a joint work with Hiroyuki Nakahara from Riken CBS and Koji Tsuda from the University of Tokyo. In our approach, we try to combine two objects. One is multidimensional probability distributions, and the other is partial order structure, which is typically represented as a directed acyclic graph. Then we can actually treat these two objects in an information geometric manifold. Then we have two important coordinates, theta and eta, and they are connected via Legendre transformation. And each data set is treated as a point in this space, and the machine learning procedure can be achieved as a projection of this point onto some submanifold. And we use this formulation for tensor decomposition. Then each tensor is treated as a point and distribution equipped with the partial order structure. Then in our approach, each tensor is treated as a point in an information geometric manifold, and the tensor decomposition process is achieved as a projection of this point on some submanifold. In our method, we find the set of parameters which approximates the input tensor, so like this. And this parameter space is determined by the decomposition basis, which is given by the user. And then from this set of parameters, we can reconstruct a tensor. And this reconstructed tensor always uniquely exists. And moreover, the Carver-Kleibler divergence from the input tensor to the reconstructed tensor is always minimized. So in this sense, our method always finds the best approximation of the input tensor. And our method can treat also sparse tensors where the zero entries can be naturally ignored. And our information geometric formulation, we have two important submanifolds. One is M-flat submanifold, and the other is E-flat submanifold. The M-flat submanifold corresponds to the set of tensors with the same expectation with the input tensor, while the E-flat submanifold corresponds to the set of decomposable tensors. Then our method, Legendre decomposition, corresponds to the E-projection, which projects some decomposable tensor to the intersection of these two submanifolds. And this projection actually corresponds to the maximum likelihood estimation of distributions. And in addition, we can analytically compute the gradients of these parameters. And these gradients correspond to the Fisher information, so we can use the natural gradient method to perform the tensor decomposition in our formulation. And this is an example of our experimental results on the MNIST dataset. Then you can see on the left-hand side the reconstruction error of the tensor decomposition methods. And our method, colored in red, shows the best performance in terms of the RMSE compared to some popular methods like Tucker or CP decompositions. So to summarize, we present Legendre decomposition for tensors. And the solution of this tensor decomposition always uniquely exists, and it minimizes the K divergence from the input tensor. And the key to achieve this decomposition is to use the dually flat manifold, which is well studied in information geometry. And we have this duality comes from two parameters, theta and eta, and they are connected via Legendre transformation. And in addition, we showed that our tensor decomposition can be viewed as an extension of learning of Boltzmann machines. And the sample space of Boltzmann machines is a kind of a special case of tensors. So if you are interested in more about information geometric tensor decomposition, please come to our poster number 92 downstairs. Thank you.
Okay, thank you everyone for coming to this session. I think we are closing, and you can all enjoy the posters now.